In chapter 4, we are going to ultimately be looking at finding the greatest common divisor and least common multiple of two or more numbers. But we're going to start by looking at divisibility. And then in the second section, we'll look at tests for divisibility. There's a couple proofs that I have in the notes that I'm not going to go over on the video here because it would literally be me just reading it out. So I want to start on the second page here with the definition of primes and composite numbers. And then also we have units. One is our unit. One is neither prime nor composite. It's all to itself. A prime number is a number that just has two factors. Only two numbers divide into a prime number, and that's 1, because 1 goes into everything, and itself. A composite number has more than two different factors. And what we're going to be doing here initially is we're going to be breaking down some numbers into their prime numbers, the product of their prime numbers that make them up. So got a little highlight from history you can read through on your own, but I want to get to this example here. It's following the fundamental theorem of arithmetic that says that we can express any natural number other than 1 as a product of its prime factors. And that product is going to be unique. So we can find these prime factors by using factor trees. So I've got these 4 examples here: 72, 126, 264, and 550. Starting with 72, we want to break it down into two numbers that multiply to equal 72. And it actually does not matter which two numbers you choose. You'll end up with the same prime numbers in the end. So I'm going to start with 8 times 9. Neither 8 nor 9 are prime, so I can break these down further. 8 is 2 times 4. 2 is a prime number, so I'm going to circle it. 4 is not. We'll keep going there in a second. Then 9 is 3 times 3, and 3 is also a prime number, so we can go no further there. The 4 breaks down as 2 times 2, and again, 2 is prime. So I now have my prime factorization. It's 2 times 2 times 2 times 3 times 3. But we usually write this in terms of exponents, so we'd say 2 to the 3rd power times 3 to the 2nd power. We can do the same thing with the other numbers. 126. Again, you can break this down any way that you like, but 126 happens to be 6 times 21. So I'm going to break it down like that. 6 is 2 times 3. Both of those are prime. 21 is 3 times 7. Both of those are prime. So we have 126 is equal to 2 times 3 times 3 times 7, which can be written as 2 times 3 to the 2nd power times 7. 264. Again, you have a multitude of ways that you could break this down. 264 is 8 times 33. That's one of those ways. 8 is 2 times 4. And of course, the 4 is 2 times 2. 33 is 3 times 11. And both of those are prime. So we have 264 is equal to 2 times 2 times 2 times 3 times 11, or 2 to the 3rd power times 3 times 11. And one last one here, 550. 550, again, there's multiple ways that you could write this, but I'm going to write it as 10 times 55. 10 is 2 times 5. Those are both prime. 55 is 5 times 11. Those are both prime. So 550 is 2 times 5 times 5 times 11, or 2 times 5 squared times 11. And that leads us to this theorem, the prime power form of the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic tells us that every natural number greater than 1 can be expressed as a product of primes in only one way. And our prime power form of the fundamental theorem of arithmetic names this as the prime power factorization of the number. So this is giving this a specific name. So at the bottom here, we're asked to find the prime power factorization of 48, 108, and 2,250. You could do factor trees just like we did to find these. I want to go over another method that you could use just to give you options for these three. So you could do a form of division. So let me start with the 48 and show you how this works. And you could start dividing by prime numbers. So the first prime number is 2, and 2 happens to go into 48, and it goes in 24 times. So I'm going to try 2 again. 2 also goes into 24, and it goes in 12 times. Try 2 again. It goes into 12 6 times. Try 2 again. It goes into 6 3 times. 3 is a prime number, so I stop. 48 is 2 times 2 times 2 times 2 times 3, or 2 to the 4th power times 3. So we can do the same thing. I'm going to switch colors here with 108 and then with 2,250. So with 108, I'm going to start again with 2. That's my smallest prime number, and 2 goes into it 54 times. 2 also goes into 54 27 times. 2 does not go into 27, but the next highest prime number, 3, does. 3 goes into 27 9 times. 3 goes into 9 3 times. Since 3 is a prime number, we stop there. So 108 is equal to 2 to the 2nd power times 3 to the 3rd. 2 times 2 times 3 times 3 times 3. For our last one, 2,250. Same exact process. 2 goes into 2,250 1,125 times. 2 does not go into 1,125, but 3 does. 3 goes into 1,125 375 times. 3 also goes into 375. It goes in 125 times. But 3 does not go into 125, so let's try the next highest prime number, that's 5. 5 does go into 125, it goes in 25 times. 5 also goes into 25 5 times. We end up with a 5, which is a prime number, so we can stop. So 2,250 is 2 times 3 times 3, or 3 squared, times 5 times 5 times 5 times 5 to the 3rd. And that's the prime power factorization.